Find the radius of convergence of the sum of k factorial times x to the 2k divided by 3k to the k power. I have the ratio rule written here, and the ratio rule says as the limit of k approaches infinity of a sub k plus 1 divided by a sub k is equal to L. If L is less than 1, the series converges. Otherwise, it diverges. Okay, so what we're going to do is take a ratio and point this k towards infinity and see what happens. Okay, so we need to sub in a k plus 1 everywhere that we see a k in this problem. There's 4 places here. Okay, and then we'll divide it by just this. Okay, this is a sub k right here. All right, so a sub k plus 1. So we are, let's first, we'll mess with the limit later. First, let's figure out what this ratio is. So let's plug in a k plus 1. So we get k plus 1 factorial times x to the 2 times k plus 1 divided by 3 times k plus 1 to the k plus 1 power. Okay, now we're going to divide by, that's what it says, divide by the original, this is a sub k, but I'm going to save a step by saying, okay, well, if I'm dividing by another fraction here, then I can multiply, but I can flip the fraction. So I'm going to write this exactly, except I'm going to flip it upside down. The 3k to the k is going to go on top, k factorial times x to the 2k is going to go on bottom. So times 3k to the k divided by k factorial times x to the 2k. All right, so I do want to, let me go ahead and put that around absolute values. I do want to take the limit of this eventually, but for right now I want to try to clean this thing up because there's a lot of k's and k plus 1s and factorials floating around, and we want to try to get rid of those. Okay, so the first thing I'm going to do is realize that k plus 1 factorial is the same thing as k factorial times k plus 1. Let me write that down. So what I'm about to do is say that, okay, k plus 1 factorial is equal to 1 times 2 times 3 times dot 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 times k plus 1. Okay, so you can see right here, this is k factorial, and then times k plus 1. Okay, so you can say that k plus 1 factorial is equal to k factorial times k plus 1. And that's going to help us reduce things, because if I change it into that right here, I'll be able to reduce it with this k factorial that's in the denominator of the other fraction. So let's go ahead and do that, and we'll also manipulate some other things here as we're going. So the first thing I'll do is write that this is k factorial times k plus 1. And then I have x to the, okay, so this is x to the 2k plus 2, right, when I distribute this. Okay, and x to the 2k plus 2 is the same as x to the 2k times x to the 2. So I'll write x to the 2k times x to the 2. Now, why did I do that? Well, I have an x to the 2k down here. So that's another thing that I'll get to reduce. Okay, and then in the denominator, I have a 3 to the k plus 1 in power, and then a k plus 1 to the k plus 1 power. Okay, so the first thing I'll write is 3 to the k plus 1. Okay, and then k plus 1 to the k plus 1 power. I'll come back to that in a minute and clean that up. And then let's just write this stuff over here. So we have 3k to the k power divided by k factorial x to the 2k. All right, so first let's reduce what we can there before we start writing anything else. Let's cancel out the k factorial and the x to the 2k. That should make things a little easier for us. Okay, so let's keep going. Let's clean some more stuff up. So this 3 to the k plus 1, 3 to the k plus 1 is the same thing as, I'll just write that underneath here, 3 to the k plus 1 is the same thing as 3 to the k times 3. Okay, so we're going to write it that way. And k plus 1 to the k plus 1 power is the same thing as k plus 1 to the k power times k plus 1. Okay, so you can see why we're going to do that. That's going to cancel right here. Okay, so let's write that in the next step. So we have, let's see, a k plus 1 on top and an x squared on top. We also have a, let's go ahead and write that other fraction, 3k to the k on top. Okay, and then on bottom we have 3 to the k times 3. And then I'll also have a k plus 1 to the k times k plus 1. Okay, obviously that one is going to reduce, and I could have actually done this one. Let's go ahead and do that. So 3k to the k power is the same thing as 3 to the k times k to the k. Okay, so let's pretend that we wrote that. That way I can go ahead and cancel out this one as well. But it leaves the k to the k power. So that gets me, and these all have absolute values. I should have written those as I went along. Okay, so that leaves us at let's see, an x squared and a k to the k power divided by 3 times k plus 1 to the k power. Okay, that's almost as clean as we can get it. We can do one more step. We can say that we have x squared over 3 times k over k plus 1 to the k power. All right, so now that I have all that, that's around absolute values, or has absolute values around it. So now I'm going to go ahead and try to take the limit. So the limit as k approaches infinity, which is what we've been doing the whole time. We're back to this, okay, but we've simplified the inside. So now I'm going to go ahead and write the limit of x squared over 3 times k over k plus 1 to the k power. Okay, so this one is still rather complicated because we have a k in the exponent. Okay, so what I'm going to do is, and I'll do this in a, let's do this in a separate color. I'm going to take a different limit, and then I'll come back to this limit. The limit that I'm going to look at, I am going to raise this to the e to the ln power. Okay, so I'm going to raise it to the e to the ln power, and when you raise that to the e to the ln of k over k plus 1 to the k power. The reason I'm going to do that is because when you, first of all, e to the ln, they cancel each other out. So the inside's the same as this, right? But this allows us to bring our exponent down. Okay, so that would be equal to e to the k ln of k over k plus 1. Okay, now if we take the limit of this, let's just take a look at that exponent. The limit as k approaches infinity of k times ln of k over k plus 1. Why does that help us? Because that still looks complicated even though we've gotten rid of the exponent. Well, we can see what happens when I plug in infinity. Well, plug in infinity. As these approach infinity, what's going to happen? Well, this one, the k value here, is just going to go towards infinity. Okay, this one, the inside will go towards 1. And what is ln of 1 if this inside turns into 1? Well, it's 0. So that's in an indeterminate form, infinity times 0. Okay, so given that it's infinity times 0, then I can use Hopital's rule on this. Okay, so Hopital's rule is what we're going to use. So first I need to write this in terms of, let's write it in terms of infinity, or 0 over 0 if we can. Okay, so I'll write it as 0 over 0. So what I'm going to do is, instead of having the k up here, I'll just divide by 1 over k. Okay, so if I do that, we already know this one goes into 0, turns into 0, and now this one is going to turn into 0 too as I send it towards infinity. So you get 0 over 0, which is why we have L'Hopital's rule. Okay, so it is an indeterminate form now. Now L'Hopital's rule says that we need to take the derivative of the top and bottom. Okay, recall that the derivative of an ln function is du over u. So the derivative of the inside divided by the inside. I'll let you take care of that, but the derivative is going to be of the top. Let me go ahead and write the limit as k approaches infinity. The derivative of the top is going to be 1 over k times k plus 1. I'll let you do that on your own. And then the derivative of the bottom is negative 1 over k squared. Okay, let's clean that up before we try to take the derivative again. So we clean that up a little bit. K approaches infinity. Let's flip this up to the top. It is negative. Okay, so we flip this up to the top when you get a k squared on top, and then you get a k times k plus 1 on bottom. Okay, now we can reduce this one more time. So reduce the exponent with this k. So that becomes a limit as k approaches infinity of negative k over k plus 1. Okay, now what happens as we send this towards infinity? Well, since the variable's k here, okay, you send this thing towards infinity, so they have the same exponent, then it's just the variables in front. What are the variables in front of these two k values? Well, there's a -1 and a 1. So our answer is -1. Okay, so the answer to this limit right here that we did when we raised it to the e to the ln power is 1. Okay, but we only took the limit of this exponent. We didn't mess with the e. Okay, so all this time we've had this e that's been floating around here. So e to the limit of all this stuff is equal to -1. So the whole thing is equal to, when we don't take the or when we put the e back, the whole thing is equal to e to the -1. Okay, so we know that this portion here, according to all this stuff in red, this portion right here has a limit of e to the -1, or 1 over e. Okay, that's the limit of that. Now, what about this x squared over 3 stuff? Well, x squared over 3 is, they're both considered constants because the only variable is k. So the limit as k approaches infinity of x squared over 3 times k over k plus 1 to the k power of this whole thing, and I'll go down here where we can see, the limit is equal to x squared over 3 times 1 over e, which is equal to x squared over 3e. Okay, so we found the limit. Now what do we do with the limit? Well, the ratio rule says that if you find the limit and let's go back and read what it says, if it's less than 1, your series converges. Otherwise, it diverges. And the problem is it's telling us that it converges somewhere. That's why it's asking us to find the radius of convergence. It's saying, where does it converge? Okay, so we're not asking if it converges, we're asking where it converges. So we need to show that this thing is less than 1, or where it's less than 1. So it's pretty simple to do that now that the hard part was taking the limit, the easy part now. So we get x squared over 3e, and we just say, well, let's make sure that's less than 1. Okay, we want it to be less than 1 because that's where it converges, so let's make it less than 1. So we can say, okay, well, that's x squared is less than 3e when I multiply the 3e over. And then x squared is, or not x squared, excuse me, let me write it over here. X is less than the square root of 3e. Okay, so your interval of convergence on this problem is the square root of 3e.